has the theme of combinatorics and randomness. We have lots of papers that talk about very fundamental problems, but at the same time have general results that can be useful in many other areas. We are starting with a paper on card guessing. Then we have a couple of papers on random bots. We have a paper on sampling and distributions. So these are all very general and very clean results that a TCS audience should appreciate and understand. And it may just be that one of the lemmas that we talked about is just the thing you need to finish your own research project. So let's start. The first speaker is Boaz Menuhin from Weizmann, and he will talk about card guessing with limited memory. So can you share your slides?
All right, so thanks a lot for the presentation and for the introduction. So I'll be telling about keep this card in mind, card guessing with limited memory, which demonstrates the power of adaptive adversaries in stream. This is a joint work with Moni Naor. So card guessing is played by two players, a dealer and a guesser. The dealer begins the game with a deck that consists of n cards. In each turn, the dealer draws a card and the guesser tries to guess it. The card is then revealed and discarded, so it can no longer be played. And the guesser gets a point for each correctly guessed card. And what we're interested in is how many correct guesses did the guesser make. And since the game is random by nature, we're interested in the expected number of correctly guessed cards. With a guesser with perfect memory can just keep track of all cards that still reside in the deck and guess from them. Just in every turn, guess a card that still resides in the deck. On the first turn, that guesser would be correct with probability 1 over n, on the second with 1 over n minus 1, and so on until the last card, which the guesser can identify correctly for certain. And by linearity of expectation, we get that the number of correct guesses is expected to be the harmonic sum, which is roughly ln n. On the other extreme, a guesser with no memory at all, the best such a guesser can achieve would result in a correct guess with probability 1 over n in every turn. So again, by linearity of expectation, we expect a single correct guess. But a memoryless guesser can also get a correct guess for certain by simply repeating the same guess over and over again, since each card must appear exactly once in the game, that guesser would be correct once and only once. These two examples are taken from textbook on algorithms by Kleinberg and Tardosh, and they demonstrate that with n bits of memory, we can achieve ln n. With 0 bits of memory, we can achieve a single correct guess, but what we're interested in is what happens in between. And our answer is that it depends much on the dealer. So we consider three kinds of dealers. The first dealer we consider is a random shuffle one. That dealer shuffles the deck properly at the beginning of the game and draws cards one by one. This is equivalent to drawing at random in every turn, or to sample a random permutation pi and draw the card pi I in turn I. The second dealer we consider is a static dealer. That dealer prearranges the deck at the beginning of the game, since that dealer may be somewhat familiar with the guesser. So in order to fail him, that dealer fixes the deck in advance, but once the game begins, the deck remains as it is. So the order cannot change mid-game. The third dealer we consider is an adaptive one. That dealer draws cards thoughtfully in an adversarial manner in response to how the guesser played so far. As for the guesser, we assume that the guesser has memory of size m and some random bits, and it is made of two functions, a card guessing function and state transition function. The card guessing function receives the memory state and randomness and produces some guess. And the state transition functions also, the function also receive a card, the last drawn card, to produce the next memory state. So, for example, one very simple technique is to concentrate on a subset of M cards with M bits of memory and pretend as if the deck consists only of these cards. Since these M cards must appear at some point, and by tracking them and guessing a card from this set that hasn't appeared, basically we get perfect score if the deck contained M cards, so we get ln M. So the guessing function is just to guess a card that did not appear, and the state transition is to flip a bit for every card that was drawn. Now, what we showed in the paper was one that there exists a guesser with only log square n bits of memory that plays very well when playing against a random shuffle dealer. Furthermore, this guesser is deterministic. So a simple adversarial argument can tell that for every deterministic guesser, there exists a bad ordering on which that guesser managed to make at most a single correct guess, as guessing the last one correctly or a single card correctly may be inevitable. So our second result is that there also exists a guesser with log square n bits of memory that plays very well against any static dealer. And by very well, I mean very close to ln m, to a guesser with perfect memory. Our third result shows that the above are optimal. So no guesser with significantly less memory can achieve similar results, basically. And our fourth result is an adaptive dealer, basically that defeats any guesser, any memory-bounded guesser. So the best the guesser can do is just to focus on a subset of cards, on the basic thing I showed in previous slide. So the best a guesser can do is to keep cards in mind, and hence the name of the paper. While we count the number of random bits used by our first two guessers, low memory guessers, our two impossibility results holds even when the guesser has crypto and unlimited randomness and is computationally unbounded. The way we do it is by using a technique called proof by encoding, which is quite general and successful method. Some notable examples were Moser and Tardosh algorithmic Lovash-Loka lemma, and proof for the success rate of cuckoo hashing, and also in oracle separation in crypto. And basically, the main ingredient for this technique is to have an encode and decode functions for some domain. And basically, what we do is construct these functions using the two guessing functions that the guesser is made of. The first mathematical piece we found on card guessing comes from a paper by a famous statistician, Ronald Fisher, from 1924, in the Proceeding of the Society of Psychical Research, where he suggested and analyzed card guessing as a method to settle one's claim for having clairvoyance or telepathy abilities. But also a more decent research was conducted even lately. Our work joins a tree of works concerning adversarial streams, in that we show that there exists a streaming problem against which an adaptive adversary basically can defeat an algorithm. We think it may be interesting to look into the cases where the card is made also from several copies of some of the cards. And also in the case where the guesser and the dealer change places, and the dealer is the one with limited memory. We also think it may be interesting to think about practical usage of our technique, maybe for blackjack or poker. It seems very fit to finish with George Santayana's quote, those who cannot remember the past are condemned to repeat it. And we add that this holds even if you use randomness and cryptography. So thank you for listening, and thank you for the organizers.
Okay, thanks. That was a very interesting talk. If there are any questions, please type them in the chat, and you can also just raise your hand and I can try to spot you and ask you to just say them out loud. Another thing, the questions already come in, but another thing is, Jan, can you try and start sharing your slides so that we don't have a break between the two talks? Okay, so the first question is, do you think your techniques could adapt to lower bounds for some streaming problems in adversarial settings?
So basically, I think the answer is yes, but it depends what you consider as lower bound, because it's like, it depends how you look at it. If you're talking about impossibility results, then yes, that's exactly what we do in the paper. So definitely. And if you want to discuss a more a specific problem, I'll be happy to discuss it later.
Okay. I also have a quick question, maybe just how crucially does your result depend on the cards being distinct in the deck? Maybe I tell you that one card appears twice, what will change?
Right, that's an excellent question. So I went over this very briefly. There is the case where there are several copies of the cards. That's the case I think you're talking about. So our algorithm doesn't scale well with the number of copies. And in fact, if there are too many copies, our algorithm performs even worse than a memory-less algorithm. So I think that's a great open direction to go into.
Okay, so thanks for the talk. For the future talks, if there are any questions, you can also put them in the chat during the talk, and I will see if I can interrupt the speaker. And if not, I'll just take them at the end. So the next speaker is Jan from Stanford, and he will be talking about a Gaussian fixed point random walk.
Sorry, give me 1 second. Apparently Adobe wasn't working, which is weird. Okay. Does this work? Are you kidding?
We see our thumbnails on the left.
Yeah, I'm not sure how to remove those. Sorry.
Maybe go to, there's a 3 bars on the top left.
Yeah, okay, there you go. Okay, thank you. Okay, can I get started? Okay, so hey everyone, I'm Yang, and today I'm going to be presenting work on a Gaussian fixed point random walk. This is joint work with Ashwin and Mehtaab Sawhney at MIT. So before talking about a Gaussian fixed point random walk, I'm going to introduce the problem, which was the motivating problem for this work. The problem studied is online vector balancing, where vectors v1 through vt, which are n-dimensional, arrive one at a time. Our goal is to assign signs epsilon1 to epsilon t, each of which is plus or minus 1, to maintain a small discrepancy. In other words, we want to keep the quantity max over all prefixes of the signed partial sum, that vector, the L infinity norm of that vector is small. In general, discrepancy theory has had numerous applications, including balancing covariates in randomized controlled trials. and online NV minimization. In general, algorithmic discrepancy has been a very active field. Since about 10 years ago, Bonsall and Lovett-Mecca gave a polynomial time algorithm to compute signings for the 6 standard deviation suffice result of Spencer. Just to get some intuition for how an online vector balancing procedure can go, in the procedure, we first get a vector, and then we assign it a sign, and then we maintain the partial sum. Then we get the next vector, and then our algorithm has to assign a sign, and then we update the partial sum, and we keep going. As you see in this process, the algorithm has to take the input vector and assign a sign before seeing the next vector. So in that sense, it's more general than the offline discrepancy problems where you get all the vectors immediately. For the purposes of this talk, we're going to focus on the case where all the vectors are bounded in L2 norm. Additionally, we're going to assume an oblivious adversary. In this setting, all the vectors v1 through vt are fixed beforehand and do not change based on the randomness of the algorithm. However, the algorithm still has to assign the sign epsilon I before seeing the next vector vi plus 1. So as mentioned, this model generalizes the offline setting where all the vectors vi are revealed at the beginning and we get to assign the signs after looking at all the vectors. Finally, the oblivious adversary model is a natural model because for adaptive adversaries, you can show a square root t lower bound. And that's because what the adversary can do is pick the next vector vi plus 1 to be orthogonal to the current partial sum maintained. So then the L2 norm of the vector will go up by 1 every step, no matter what our algorithm does. To put our results in context, it's useful to mention some previous results. So one benchmark we can compare previous results against is this Komlosh conjecture, which is an open problem in mathematics. The Komlosh conjecture asks whether given vectors v1 through vt in n dimensions, all with the L2 norm of most 1, whether there exists signs to get the L infinity norm of the signed partial sum of all the signs of the signed sum to be a constant. There's additionally an even stronger version of this, which is, well, what I'm going to call the Komlosh conjecture for prefixes, which asks, given vectors v1 through vt in n dimensions, all with L2 norm of most 1, whether there are signs that actually make all L infinity norms of all partial sums of all prefixes a constant. So both of these are open. It's not known whether they're true. However, the following results are known. You can show an upper bound of square root log t for the prefix version. This is a result due to Banaszczyk. However, Banaszczyk's result does not run in polynomial time. It's non-constructive. In terms of polynomial time algorithms, it's known how to achieve a square root log t bound for the total sum, but not all prefixes. And finally, it's known how to achieve an O of log t bound for prefixes. I think you can show this using results of Bonsall or Lovett-Mecca. But additionally, if you design an online algorithm, it will naturally get a discrepancy bound for all prefixes, and that's the best known. You can get an O of log t bound for all prefixes in an online manner. Towards these problems, here's our results. So while we don't show the maybe dream or optimal version of this, which is an O of square root log t bound for all prefixes in an online setting, we do show the following. So we show that in the Komlosh setting, so this is where all the vectors have L2 norm of most 1, and they arrive in an online manner. We give an online algorithm against oblivious adversaries, and we assign signs of either -1, 0, or 1, and very few of the signs are 0. So at most 4% of the signs are 0, and we achieve a discrepancy of square root log t with high probability. So square root log t is kind of like the discrepancy you expect from Banaszczyk's bound. However, our algorithm outputs some zero signs 4% of the time, so it doesn't actually get all the way there. And in our second result, we show that there's an online algorithm against Glivi's adversaries that selects signs either -1, 1, or 2 that also achieve discrepancy square root log t. So once again, it doesn't only assign signs -1, 1, as you would expect for a discrepancy problem, but it assigns a possible extra sign, but it achieves the square root log t discrepancy. So just a couple corollaries or discussion. So using the first result on partial colorings, you can recover an O of log t bound for online discrepancy by just recoloring the signs that were assigned 0. So as noted, this falls short of matching Benastrix bound online and for all prefixes because of the additional 0 or 2 signs allowed. However, I think these results have made us much more optimistic that a square root log t online or prefix discrepancy with polynomial runtime, like only ±1 signs, kind of this like dream or optimal result. We do believe it's achievable with ideas along the same lines, but we're not really able to analyze the algorithms that we're trying to design. Okay. So now let me describe how we achieve these results. And we achieve these results by designing a random walk, which might be independently interesting, which we call the Gaussian fixed point walk. What we precisely show is that there is a Markov chain on R whose steps are -1, 0, 1 or -1, 1, 2. And there's almost a 4% probability of picking 0 each step. And the stationary distribution is exactly the normal distribution in 1 dimension. So this is all 1-dimensional. From this, we can design an online discrepancy algorithm in the following way. Let's consider just the case where all the vectors of L2 norm 1. So what we do is we initialize a starting vector from the n-dimensional normal distribution. So when Vi arrives, we decompose the n-dimensional normal distribution into 1-dimensional Gaussians in the direction of Vi, and then we simulate the Gaussian fixed point random walk on that one direction, and we update the vector accordingly. To show that this works, all you need to show is that the distribution of the partial sum Wi is exactly normally distributed each step. Therefore, our partial sum is the difference of two possibly coupled Gaussians with distribution n 0i, and therefore the infinity norm is square root log t with high probability. I wanted to discuss why we need this extra 0 sign. And the reason is because we can actually show that there's no Markov chain on Z, so 1 dimension, with steps -1, 1, whose stationary is exactly proportional to the Gaussian. To show that, if such a chain existed, then the total mass on the even integers and odd integers has to be the same, but that's just not true. So that's why we don't know how to design a walk with -1, 1, and we need this extra 0. Okay, so let me just wrap up. There's several relationships to previous works I'm just going to put up here but not really discuss. So in terms of future directions, I'm wondering obviously if we can design a square root log t discrepancy bound with signs -1, 1 for all prefixes, online, etc. Or even easier, can you design a polynomial time square root log t discrepancy bound for all prefixes, even in an offline setting? And finally, are there other applications of this Gaussian fixed point walk? Yeah, that's all I had.
Okay, thanks, Jan. If there are any questions, please feel free to put them on the chat or just raise your hand. In the meantime, Luca, maybe you can share your screen. I was curious, you wanted to get a result without any zeros, but you get like 4% of the zeros. Does it affect any of the applications?
So in general, in discrepancy theory at this point, it's come down to being very careful about getting the number of log factors right. I think for a lot of, especially after these results, unlike recent results on oblivious online discrepancies. So in that sense, yeah, it's like doesn't get the number of log factors correct. Okay. I haven't looked into applications beyond that. But.
Okay, interesting. Okay, thanks again. The next speaker is Luca from the University of Bath, and he will be speaking about geometric bounds on the fastest mixing Markov chain.
Thanks for the introduction. So this is joint work with Sam Olesker-Taylor, also from the University of Bath. So let me introduce what is the fastest mixing Markov chain problem. As input, we have a finite graph undirected, and our goal is to sample from the uniform distribution over the vertex set of this graph. And the common strategy to do so is to construct a Markov chain on the vertex set of G that has a uniform invariant distribution and that sort of respects the topology of the graph. And with this, I mean that the transitions between states are allowed only across edges of the graph. And for this algorithm to be as fast as possible, we would like the mixing time of this Markov chain to be also as fast as possible. So let me be just slightly a bit more formal. We can formalize the fastest mixing time on a graph as a minimization problem, where we are minimizing overall transition matrices over the vertex set of the graph that have uniform invariant distribution and that respects the locality, the topology of the graph. And when I will be talking about mixing time, I will always be talking about the total variation mixing time. This problem has been introduced by Boyd, Diaconis, and Xiao in 2004, but there has been a few works since. However, all this work focused mainly on finding alternative formulations of the problem or finding relaxation for the problem, or even like studying specific classes of graphs, such as the fastest mixing Markov chain on a path. What we want to do is something a little bit more general, in my view, in the sense that we would like to characterize what kind of graphs admit fast mixing. And our first main result essentially shows that vertex conductance characterizes fastest mixing of a graph. So let me introduce the notion of vertex conductance. Given a subset S of vertices, its vertex conductance is just the ratio between the vertex boundary of the set divided by the size of the set. And we can define the vertex conductance of the whole graph as the minimum vertex conductance of a set of vertices of the graph. What we show is essentially a Chigger type result that relates the fastest mixing time on a graph to its vertex conductance. In particular, we show that the fastest mixing time is sandwiched between the inverse of the vertex conductance and the inverse of the vertex conductance square times a polylog factor. And if you remember, Chigger inequality essentially says that the mixing time of the simple random walk is related to the edge conductance of the graph. So we have something similar, but instead now we are considering not the mixing time of a specific walk, of a specific chain, but the fastest mixing time of all chain and its relation to the vertex conductance of the graph. So let me just show you briefly an example. Here we have two cliques connected by a perfect matching, cliques of n vertices. The simple random walk mixes poorly on this graph. It takes order of n time to mix. However, the vertex conductance of this graph is almost optimal, is a constant, independent of n, and indeed also the fastest mixing time is a constant. And how do we show that? Well, essentially, you just need to consider a simple random walk on a reweighting of the original graph, where essentially we have upweighted the edges between the two cliques. Okay, let me just say two words about the proof. So the starting point of the proof is to relax our problem. Instead of optimizing for the mixing time, we optimize for the spectral gap of the transition matrix as a proxy of the mixing time. And it turns out that this optimization problem can actually be recast as a semi-definite program. And so we can apply duality, and we can obtain this variational characterization that was, let's say, discovered by R. And I don't want to go into the details of this. I just want to highlight the fact that this is the minimization over two functions, G and F. However, if we fix the function f, what we obtain is just a linear program. And this linear program is actually the dual LP for a fractional matching problem on a graph that is obtained from the original graph G by reweighting the edges in a particular way. And this prompts us to introduce this new concept that we call matching conductance. Its definition is similar to the vertex conductance. However, here we are not counting the vertex boundary of the set. What we are counting is we take the set S, we look at the edges between S and its complement, and we compute the maximum weight matching over the edges. And what we show is essentially a Cheeger type inequality that relates the optimal spectral gap to this matching conductance of the graph. So what does this have to do with vertex conductance? Well, it turns out that matching and vertex conductance are the same apart from up to a constant. They are of the same order. So if you prove a Cheeger type inequality for one, you obtain a Cheeger type inequality for the other. So now you will ask, but why introduce the matching conductance in the first place? Why not using the vertex conductance directly? Well, the reason is that, yes, globally matching and vertex conductance are of the same order. However, if you look at a specific set S, the matching conductance of S might be much smaller than the vertex conductance of S. And so to apply the let's say Cheeger machinery, you actually need to exploit this matching conductance. And this is essentially what I wanted to say about the proof of this result. So essentially, up to now, what we have shown is that vertex.
Sorry, before you proceed, there's a question. Have you thought about getting a tighter bound on the mixing time by bounding the modified log Sobolev constant of the watt instead of the spectral gap?
I didn't think about it that much in the sense that it came to my mind, but I guess we exploit this SDP duality, and I don't know, can you, I'm not sure you can recast log Sobolev as an SDP, but maybe you can, and in the case you might obtain. But I think what you would get is still, yeah, you would get still instead of. I don't think it would help that much, to be honest, because we lose a factor of log n because of an application of Johnson-Linde-Strauss, and then the other log n factor, it's sort of needed because in Cheeger type results, it's needed when you bound mixing time. And so you would have the same, I think, bound with respect to the vertex conductance, but I'm not sure. I don't know if that makes sense. Okay, thanks for the question. Okay, so where was I? So so essentially we have shown that to admit fast mixing, a graph needs to have a relatively large vertex conductance. So we sort of ask ourselves, can we actually obtain a fast mixing Markov chain on a graph with small vertex conductance if we relax a bit the requirement of the fastest mixing Markov chain problem? And the answer is yes, by considering the following relaxation. Instead of asking for our Markov chains to mix precisely to the uniform distribution, what we ask is for our Markov chain to have an invariant distribution that is epsilon close in total variation distance to the uniform distribution. And then we show that it's always possible to construct such a chain that mixes in time that essentially depends quadratically on the diameter. And this might be much better than the vertex conductance bound. An example, the Dunbar graph, 2 cliques of n vertices connected by single edge. Here, the vertex conductance is quite poor, is order 1/n, and so the fastest mixing is also order of n. However, if you look at the diameter is very small, is just a constant. And indeed, you can construct a chain that mixes in time that is essentially independent on n. And you do that by considering a spanning tree of the graph, carefully reweight this spanning tree, and then perform a simple random walk on this reweighted graph. Okay, so let me conclude. What we have shown essentially is that 3 geometric quantities characterize the mixing properties of the graph. It was already known by Chigre inequality that edge conductance characterized the mixing time of the simple random walk. What we've shown is that the vertex conductance characterized the fastest mixing time on the graph, while the diameter characterized the fastest almost mixing time of the graph. There are several questions left open by our work. I just want to mention one. This relation between edge conductance and the mixing time of the simple random walk has been quite fruitful from an algorithmic point of view. Can our results also spur some algorithmic result? We are not sure, but we would like to find out. Thank you very much.
Okay, thanks for the talk. Dimitrios, maybe you can start sharing your screen. And if there are any questions for Luca, feel free to ask them.
Hi.
Hi.
Yeah, go on.
So you mentioned the Johnson-Lindenstrass lemma. So do you think that you can replace GL with different type embedding to improve the log n dependency?
Yeah, essentially the problem is that you might be able to improve and get rid of the log n factor, but you can only get you cannot get rid altogether of this factor, in the sense that you need a log of the maximum degree of the graph at least. Otherwise, something called the small set expansion conjecture would be wrong, and this would be like a quite I don't know if unexpected, but like right now we don't know how to prove or disprove this small set expansion conjecture. So I think a log d max maximum degree factor is needed.
Do you know what is the contractual mixing time? Does it need to be log n square, or is that expected to be lower than log n square?
Okay, so there should be a log d max in the relation with the spectral gap, and then we get a log n factor, because when you go from the spectral gap to the mixing time, you lose a log n factor.
Right, but let's say if you can bound the MSI constant, then to go from MSI constant to the...
I think maybe remaining questions can be taken offline.
Okay, yeah, sorry.
Two more speakers. Okay, so the next speaker is Dimitrios from the University of Cambridge, and he will be talking about balance allocations with incomplete information.
Yes, thank you. So my name is Dimitrios Los. I will be presenting balanced allocations with incomplete information, the power of two queries. This is joint work with Thomas Sauerwald from the University of Cambridge. So we'll start with some background on balanced allocation process, in particular sequential balanced allocation process. So we are given m tasks or balls, and we need to sequentially allocate them into n machines or bins. And the goal is to minimize the maximum load. So in this load configuration, the maximum load is just 5. And minimizing the maximum load is equivalent to minimizing the gap. The gap is the distance of the maximum load to the mean. So in a centralized setting, this problem is trivially solved using round-robin allocation. But in decentralized settings, we look for a process that assume large coordination between the bins. And this finds applications in hashing, load balancing, and routing. So the simplest of these processes is the one-choice process. So for each ball, you pick a bin uniformly at random, and you allocate the ball there. It is well known that in the lightly loaded case, that is when the number of balls is equal to the number of bins, the gap is log n over log n with high probability. And here with high probability, we mean probability at least 1 minus n to the minus c for some positive constant c. In the heavily loaded case, that is when the number of balls is much more than the number of bins, then the gap is square root m over n times log n. So you can think about this as the maximum of n independent Poisson random variables. A great improvement is the two-choice process, where for each ball, we sample 2 bins uniformly at random, and we place in the least loaded of the 2 bins. In the lightly loaded case, this process has a log n gap. So this is approximately an exponential speedup over one choice. In the heavily loaded case, the improvement is even more dramatic because the gap bound remains the same with high probability, and there is no dependence on m. There are several other processes, like the 1 plus beta process, which interpolates between two choice and one choice with probability beta. Mitzenmacher interpreted this process as two choice where when making their comparison, there is a probability of making an error. And Perez, Talbot, and Vrider proved that in the heavily loaded case, the process has a gap of log n over beta, when beta is sufficiently large and bounded away from 1. Our results also imply tighter gaps for when beta is close to 1. So when we are doing most of the time two choice. So let's look at the process we focus on our work. So the first process is the adaptive one threshold process. So based on the entire load distribution, we pick a threshold. Then we sample a bin. If the bin is has a load that is below the threshold, then we allocate there. Otherwise, we pick another bin uniformly at random and we allocate there. Of course, the second bin could be worse than the first one. And Feldheim and Georgievich determined the optimal threshold for the lightly loaded case, and they showed the gap of square root log n over log n with high probability. They also conjectured that this gap bound holds in the heavily loaded case. Also, it was recently shown that in the heavily loaded case, when the threshold is equal to the mean, then the process achieves a log n gap. A very related process is the one quantile process. So based on the entire load distribution, instead of picking a threshold, we pick a quantile. Then if the bin sampled is above the quantile, then we allocate the ball there. Otherwise, we allocate randomly. And it's easy to see that the adaptive quantile process can simulate any adaptive threshold process. And it's also possible to see that if we mix two adaptive threshold processes, then we can simulate any quantile process. And both of these are special cases of two thinning, where we pick a decision criteria of whether to accept the bin based on the entire history of the process. And there are extensions of two thinning where you take up to D samples and you have a decision criteria of whether to accept a bin or reject it. And another different way to interpret one threshold process is as two choice with incomplete information. So when we pick the threshold, we can only distinguish two bins if one is below the threshold and the other one is above. So these two bins we can distinguish, these two bins we cannot, and these two bins we cannot distinguish. And there is a similar interpretation for one quantile, but now the regions are in the rank space. So if one is above the quantile and the other one is below, then we can distinguish. Otherwise, we cannot. And based on this interpretation, we can split the load space in more regions. For example, if we use 2 thresholds, we split the load space in 3 regions, and we can only distinguish 2 bins if they're in different regions. So these 2 bins are in different regions, and these 2 bins are in the same region, so we cannot distinguish. And Weizmann and Kawashi showed that analyze the lightly loaded case for when we're using equidistant thresholds. But in our work, we mostly focus on the heavily loaded case. And it's also possible to do this for K quantiles, splitting the rank space in more regions. So our results, the first one was to disprove the conjecture by Feldheim and Gürtel-Gürvich and show that any adaptive one quantile or one threshold process has a gap that is omega log n over log n in the first n log squared n rounds. And on the positive side, we introduced a K quantile process where the quantiles are independent of the load distribution, and this achieves a K times log n to the 1 over K gap. So for K equals 1, we have a log n upper bound. For K equals 2, we have a square root log n upper bound. And because of the lower bound that we have, this difference here we term as the power of 2 queries. So this almost quadratic speed up. And then if we take K equals 3, we get cube root of log n and then 4th root of log n, and it approximates to choice. In particular, for K being log n, we recover the 2 choice upper bound on the gap up to multiplicative constant factors. Also, by majorization, we're able to analyze the 1 plus beta when beta is very close to 1. In particular, when beta is 1 minus poly n, then the gap is also log n. And by majorization, we also introduce an adaptive dethinning process, which achieves similar gap bounds. Furthermore, we're able to analyze 2 choice in graphical allocations in dense expander graphs and prove log n gap. And this makes progress towards the second open question by Perez, Talvar, and Wieder. Finally, we think our results might be useful for analyzing other randomized processes. In particular, we use layered induction over super exponential potential functions. So just a brief overview of what this is. So Perez, Talvar, and Wieder used the hyperbolic cosine potential, which basically has an exponential term for the normalized load and for the negative normalized load. And this is smoothed by a factor alpha. So in the 1 plus beta process, alpha is theta of beta. And Perez, Talvar, and Wieder prove that on any possible load configuration, this potential drops when it is sufficiently large. And by using induction and the Taylor law of expectation, one can show that the expectation of the exponential potential is at most C times n, where C depends on C1 and C2. And then using Markov's inequality, one can get an upper bound on the gap by noting that each of these terms must be strictly positive. So, and the gap we get is log n over alpha. So when alpha is small, it is easier to prove the drop, but the gap bound is worse. And they used alpha that's at most a constant. So the tightest gap bounds they could obtain were log n. So in our work, we use super exponential potential functions, which basically means that alpha can be super constant. However, the decrease does not follow at any step arbitrarily. So we have to condition on a smaller super exponential potential being linear. And for this, we develop a technique which might be general. So if you have a linear expectation on an exponential potential function, then how to convert this into a high probability result. And there are several open questions, like what are the lower bounds for adaptive k-quantile process? Is it possible to prove similar upper bounds for the k-threshold process? And is it possible to analyze the two-choice process in different noise conditions? So thank you very much for listening.
Thank you. We can maybe squeeze one question while the next speaker sets up. So I guess we have none. I had one question that came to my mind when I read the abstract. It seems that the improvements are very fine. They're about log factors and sometimes doubly logarithmic factors. Do you have something to say on this? Is it really crucial to have these? What is your opinion on this?
You mean between one quantile and two quantiles?
Actually, I meant something like the previous best known versus your result.
So the previous best known, you mean, was in the lightly loaded case. In our work, we mostly focused on the heavily loaded case, which is for arbitrary m.
I see. Then maybe I remember the lightly loaded case. Okay, thanks. So our next speaker is June from Stanford, and she'll be talking about domain sparsification of discrete distributions using entropic independence.
I thank Raghuvansh for the introduction. So this year, I work with Weizmann, Nima, Anari at Stanford, Michal, Derezinski at U Michigan, and Elizabeth Yang at UC Berkeley. I think Elizabeth in the audience. So I will start with a motivating example problem for this work. So consider this problem of sampling from element from 1 to n, given some weight p1 to pn. So that the probability of output the element I is proportional to pi. So here's an illustration with the blue column represent pi. So there's a built-in Python function to do this. This function has a optional argument called cumulative weight, which is the array where the element, where the jth element is the sum of pi for I going from 1 to j. So with cumulative weight, we can reduce the sampling time from order n to order log n. So say if you want to provide k sample from this problem, then you can first compute the cumulative weight in time order n, and then you can produce k subsequent sample in time k time log n. So the wisdom from this is like we can produce samples in much faster amortized runtime using this trick of like computing the cumulative weight first. So now our question is, can we do the same for other distribution that has exponential support size? So remember, this distribution has support size just n, so we can always pre-compute this array of cumulative weight. But what about distribution that has very large support? So a concrete way to formalize this problem is like, so consider this. So say you are given a discrete distribution mu, that is a distribution over size k subset of a ground set of size n, and you want to either sample or approximately sample from mu. And by approximately sample, I mean to produce a sample from a distribution mu prime that is close to mu interpretive distance. So the question is, how much time do we need to produce one sample from mu? And in general, you shouldn't expect to get faster than like n choose k time, because what if mu is support on just one element, then it takes you like n choose k time to even find this element, right? But our hope is that like for certain family of mu, and then after some pre-processing step, we can reduce the domain size, that is the size of the ground set from n to some set t of size much smaller than n. And then we get improved runtime for sampling from mu. So this framework of reducing amortized sampling time through pre-processing is very useful for counting problems. Because for counting problem, we have this kind of framework where we need to repeatedly sample for mu to say estimate the support size of mu. Okay, so example distribution where this domain specification framework has proven to be useful include the distribution over spanning trees or forests, or over fixed size matching of a graph, and something called determinant point process. So to remind people of some basic graph theoretic definition, a spanning tree of a graph is a set of edges that form a connected and loopless subgraph of the original graph. So here the orange edges form a spanning tree of this 7 vertices graph, and a k matching is a set of k edges in a graph such that no two edges share the same endpoint. So here the orange edge form a 2 matching. And determinant point, so the distribution that we care about in this case are the uniform distribution over spanning tree or over fixed size matching of graph. Determinant process is the generalization of this uniform distribution over spanning tree and over fixed size matching. So a k-determinant process is defined by matrix L of size n by n, where the probability of a set S is proportional to the minor of the submatrix index by S. So here, like when S is a set 1, 2, 4, then the probability of this set S is proportional to the determinant of the submatrix color in red here. So the traditional focus with DPP are on matrix L that are symmetric, so L equal L transpose. But recently, people have started to study non-symmetric matrix L for their enhanced modeling power. And both determinant point process with symmetric matrix L and non-symmetric matrix are useful for many applications, including recommender system in machine learning, image search, and generally in random linear algebra. And you can look at these reference to find more application of determinant point process. So I will briefly state the background of our work. So this framework of domain specification start with a work by Derezinski and Calladero, Derezinski, and Vuong, where they apply this framework for sampling from symmetric determinant point process. And then last year there was a fourth paper by Nima and Michal, who expand this work to sample from on log concave distribution. So our work generalized these two previous works by expanding to the class of entropic independent distribution. And this class include all the distribution considered in previous work, and in addition also include the distribution over fixed size matching and distribution on non-symmetric determinant point process. The notion of entropic independence was introduced last year by Nima, myself, and some other co-authors, and it turned out to be the right definition for this domain specification framework. So we will first define what is entropic independence. So for distribution mu, define the generating polynomial of mu to be the polynomial over n variable z1 to zn. That is the sum of mu s time product of zi for I in S. So think of this polynomial f mu as a way to extend the distribution mu to the R to the n support. Sorry. So a distribution is called entropic independent if the generating polynomial of mu applied by some transformation is upper bound by the tangent at 1 of this transformation. And now we're ready to state our main result. So we say that when the distribution mu is 1 over alpha entropic independent, then basically we can always reduce the task of sampling from domain upside n here to domain upside n raised to 1 minus alpha, and he uses thing of alpha as some constant between 0 and 1. For example, alpha can be 1/2 or 1. The application of this theorem include many faster algorithm to either sample from or count the support of various distribution that I discussed. So we have faster algorithm to count psi-k matching in planar graph. So n here that there is a number of vertices in the graph. So this is actually sublinear for dense graph. And we have faster algorithm to sample from non-symmetric KDPP. And for symmetric KDPP, we actually had some subsequent work that take some idea from this work and improve the sampling time and the pre-processing time to be practically optimal. And more generally, we found that like for any distribution after pre-processing, we can always reduce domain size from n to n raised to 1 minus 1 over k. And this actually matches the birthday paradox threshold. So if you think of distribution over size2 subset, then we always reduce the domain size from n to square root n. And we know that we cannot do better, because if we reduce to below square root n, we may not even get any set in the support of the distribution at all. So conclusion is that our work generalized and improved on the previous work by Nima and Michal. And we found that the entropy independence is the minimum assumption for the domain sparsification framework to succeed. And we also have Thai lower bound construction for the size of the domain. There's some open problem about reducing reducing the sampling time for a more restricted class of fractionally log concave distribution. But this class is still included on the distribution that I previously discussed. And if we can obtain this, then we would get more efficient algorithm for this problem of sampling from non-symmetric DPP and other related distribution related to determinable point process. And this will also be another way to channelize the previous work by Nima and Michal. Okay, that's the end of my talk. Thanks for listening.
Thank you. I have a question. I understand the birthday paradox found, so that says that you cannot get better than n to the 1 minus 1 over k. But can you also say what is stopping you from applying your transformation twice? First, I get to n to the 1 minus alpha, and then I do it again to get something smaller.
So I think the problem with this is like after you reduce domain size to n to 1 minus 1 over k, you just don't get a distribution at all. So it's like when you reduce it for the first time, you when it get 1 minus 1 over to 1 minus 1 over k, you may get a distribution that only have one set in the support, that is distributed over a single set S in contained in n to the 1 minus 1 over k. So I guess then the task will you no matter how you want to specify, you need to first find the set S. So like it just doesn't make a lot of sense to think about like specifying it further when your distribution is to the point that it is a singleton distribution.
Wait, but if it's only one set, why can't I just remove everything that's not in the set? And
but then you have learned everything about the distribution, right? Like you probably know everything about the distribution. So if you can remove everything outside the set, then you already know what the distribution look like. So maybe you don't need to pre-processing further. You just output the single set like in your distribution. So yeah, I think you are right that like you can always theoretically reduce to size to like a distribution of size like to a domain of size k by just specifying to this point and then find out the only single useful set. But I guess this point is more like a general comment. I think this domain specification from 1 to 1 minus 1 over k is not so useful, because like so I think it's become too general that like after you reduce to n raised to 1 minus 1 over k, sometimes you cannot, sometimes the problem of sampling from this distribution become very hard, like exponentially hard. So that the gain you get from this pre-processing step is not meaningful. I think you should focus more on the case where you have like alpha entropy independence with alpha around like some constant, and then you will get like sufficiently like you get like n to the raised to the 1 minus alpha domain size, and then you will get actual gain in your sampling in your sampling time compared to this.
Okay, thank you. So they were all great talks. Let's thank the speakers one more time. I'm sorry we went a little over time, but that only happens when the talks are interesting. So it's a good sign. Okay, thank you. That's this session. See you in the remainder of the conference.